Now that we know how to use L'Hopital's rule with limits of quotients, let's try and apply it for limits of products. Okay, so let's say we're trying to find the limit as x approaches 0 from the positive direction of x times the natural log of x. Okay, so if we were to plug in 0 for x, we would get 0 times the natural log of 0. So if we think about this natural log of 0, we're saying that e raised to some power, or I'm not going to write that down, let's do x, e to the power of x equals 0. There's no value for x that's going to give us 0. No matter how small x is, we can get 0.00001, but nothing's going to quite be 0. So that's going to be an indeterminate form. Anytime we have like 0 times infinity or infinity times infinity, 0 times 0, anything like that, we're going to use L'Hopital's rule. Okay, so instead of writing it as a product, let's rewrite this as a quotient because we know how to use L'Hopital's rule with quotient, so let's just rewrite it. This can be rewritten as the limit as x approaches 0 from the positive direction of the natural log of x divided by 1 over x. So remember, we can take this bottom, bring it out, flip it, and multiply it. So this is the same as x times the natural log of x, dividing by the reciprocal. Okay, so now if we plug in x, we're going to get the natural log of 0, which is undefined, divided by 1 over 0. So both of those are undefined. We're going to have to differentiate the top and the bottom. So we're going to have d by dx of the top divided by d by dx of the bottom. So we're going to get the limit as x approaches 0 from the positive direction. The derivative of the natural log of x is just 1 over x. And the derivative of 1 over x, that's like the derivative of x to the negative 1. So if we use the power rule, it's going to be negative x to the negative 2. So that's the same as negative 1 over x squared. And we can rewrite this. We can bring this out and flip it. We can get the limit as x approaches 0 from the positive direction of 1 over x times the reciprocal of the bottom. So times negative x squared over 1, or just x squared. So this is going to be the limit as x approaches 0 from the positive direction of negative x. Okay, and as x approaches 0, we can just plug that in. This is going to be negative 0, which is just 0. So that's going to be our answer for the first one. Okay. Now for the second one here, we can do the same thing. We're going to make this a quotient. Okay, so if we were to plug in negative infinity for x, we'd have negative infinity squared times e to the negative infinity. So this would give us positive infinity because we're squaring a negative number. And this would give us 0 because we're basically saying 1 over e to the positive infinity. So that's just infinity times 0, and that's undetermined. That's an indeterminate expression. So we can rewrite this as the limit as x approaches negative infinity of x squared divided by 1 over e to the x, or just e to the negative x. Okay, that's going to be the same as, well, let's think about it. If we were to plug in negative infinity for x right now, we would get negative infinity squared for this divided by e to the negative and negative infinity. So we're going to have to differentiate the top and the bottom here. Use L'Hopital's rule. So the derivative of x squared with respect to x is 2x divided by, well, the derivative of e to the negative x is e to the negative x times the derivative of the exponent, so just times negative 1, right? That's that chain rule. And if we were to plug in negative infinity for x now, we would still get an indeterminate expression. So we'd have to apply L'Hopital's rule again. We can use it as many times as we need. So the derivative with respect to x of 2x is just 2 over, so the derivative, let's see, d by dx of negative e to the negative x, we're going to get negative e to the negative x times negative 1, so that's just going to be positive e to the negative x. Okay, and if we have negative infinity in for x now, it's going to be 2 over e to the negative infinity, which is going to be 2 over e to the positive infinity, which is just 0. So 2 over infinity is always 0, any constant over infinity. Okay, next one here. Limit as x approaches 0 from the positive direction of sine x ln x. Okay, so we're going to write this as a quotient again. Every single time we're going to write it as a quotient because we know how to use those in L'Hopital's rule. And there's this plus here just because we can't approach 0 from the negative direction for using ln x because the natural log of x only exists from x equals, or x is greater than 0. It can't be less than 0. Okay, so we're going to write ln x divided by 1 over sine x. Or we could write just sine to the negative 1. That might be a little easier. Sine x to the power of negative 1. Okay, if we were to plug in 0 for x, we would get the ln of 0 over 1 over sine 0. So this is like an undefined number over 1 over 0. So it's undefined over undefined. We're not going to get an expression we can work with and find the limit for that. So we're going to have to use L'Hopital's rule, differentiate the top and the bottom. So it's going to be the limit x approaches 0 from the positive direction. The derivative of ln x is just 1 over x divided by, so sine to the negative 1, if we're taking the derivative, we're going to use the power rule here. So it's going to be negative sine x to the power of negative 2. So it's going to be negative 1 over sine squared x. Negative 1 over sine squared x. Okay. Now what we're going to get is, if we plug in 0, we're still going to get an undetermined answer. So we can kind of simplify this a little bit. This is going to be 1 over x, we can go times negative sine squared x over 1. So this is just the same as negative sine squared x over x. So we're going to get negative sine squared x over x. If we were to plug in 0, we would still get an undetermined answer. So we can differentiate the top and the bottom again. This is going to be the limit as x approaches 0 from the positive direction. Okay, we differentiate the top and the bottom again. The bottom is just going to be 1 because we're differentiating x. So the derivative of negative sine squared x, well, we can use the product rule for that. So it'll be negative sine x times sine x. Right, so if we were to do that, if we remember our product rule here, let's just think. There's probably actually an easier way we can do this. So if we limit 1 over x, just checking our work here. So this is, oh, I see what I did. Hold on. So when we differentiated sine x to the negative 1, it is going to be negative and then sine squared on the bottom, but we just have to multiply by the derivative of the inside. So it's going to be negative cos x over sine squared x. Okay, so we can rewrite this as the limit as x approaches 0 from the positive direction, right? And we can rewrite this as, we can rewrite this when we flip it, right? We bring the bottom out, flip it, and multiply. We're going to get 1 over x times negative sine squared x over cos x. Okay, and sine squared x, that's just sine times sine. So I'm going to break that up. I'm going to go just sine x in this one and sine x in this one. Okay, and one thing that we know is that the limit of sine x over x as x approaches 0 is just going to be 1. Right? Because remember it was that weird looking function, that oscillating one, where it like started at 0 and then it got bigger, and then as x was 0 it was 1, and then it kind of flattened out again. So we know that this limit right here is 1. So it's just going to be the limit as x approaches 0, or yeah, x approaches 0 from the positive direction of 1 times sine x over cos x is just tangent, so times negative tangent x. 1 times negative tangent x is just tangent x. So we can just write negative tan x. And if we were to plug in 0 for x now, we would just get negative tan 0, which is just negative 0, which is just 0. Okay, limit as theta approaches 0 of cosecant theta minus cotangent theta. So instead of getting right into the quotients, let's just think about what cosecant means. Cosecant is really just 1 over sine theta minus, and then cotangent is just cosine theta over sine theta. Okay, so if we were to plug in 0 for theta right now, we would just get 1 over 0 minus 1 over 0. Okay, so we have an undetermined or an undefined number minus an undefined number. We can't do that, so we're going to have to differentiate the top and the bottom for both of these ones here. Okay, so what we're going to do first, let's just see. We can make this one single fraction. Okay, so we're going to go the limit as theta approaches 0 of 1 minus cosine theta over sine theta. Okay, and we have to recognize that if we were to plug in 0 for theta right now, we would get 1 minus 1, right? Because cosine 0 is 1, and we're not going to be able to do that. So we're going to have to differentiate the top and the bottom here. So we're going to use L'Hopital's rule, differentiate the top and the bottom. Okay, now we're going to get the limit as theta approaches 0. The derivative of 1 is just 0, so we're going to get negative times the derivative of cosine, which is just negative sine. So we're going to get positive sine divided by the derivative of sine on the bottom is just cosine. Okay, so this is just tangent. And now we can just plug in, or it's not x, sorry, just to have it. It's theta. So sine theta, cos theta, tan theta. If we were to plug in 0 for theta now, right, we would just get the tan of 0. And the tan of 0 is just 0, right? So 0 is going to be our answer. Okay, last one here. Okay, so this is a bit of a trickier one here. Anytime we have stuff like 1 plus like a constant over x raised to the x power, that's going to involve the natural number e. Okay, that's going to involve the natural number e. So let's just see here. What if we were to put in some big numbers for x? Let's say we did 1 plus, I don't know, 2 over 1,000. So let's say our x was 1,000 raised to the power of 1,000. So we're going to get 7.37 when x is 1,000. So x equals 1,000. This is going to be 7.37. Now, e is only 2.18, but let's say we were to square e. So if we were to square e, that's 7.39. So those two are super closely related. So let's see if we get e to the power of 2 for our answer. Okay, so for this question, we're going to have to make this an equation. Okay, what we're going to have to do is we're going to have to set the limit equal to y. Okay, so we're going to say, let me just rewrite this. Y equals the limit as x approaches infinity of 1 plus 2 over x raised to the power of x. Just get rid of that there. Okay, and then what we're going to do is we're going to take the natural log of both sides. So I'm going to actually move this over a bit. So if we take the natural log of y, that's going to equal the natural log, or sorry, the limit as x approaches 0, or x approaches infinity, of the natural log of all this stuff in here. So we can use our knowledge of logarithmic equations, and we can say that this is going to be equal to the limit as x approaches infinity. We're going to bring this x down in front. So we're going to say it's x times the natural log of 1 plus 2 over x. Okay? That's a totally legitimate thing to say. Now, we want to use L'Hopital's rule because if we plug in infinity for x, we're going to get infinity times the natural log of 1 plus 2 over infinity, so times the natural log of 1. So we're going to get infinity times 0, which is an indeterminate. So we can't just do that. We have to get this into a quotient. So we're going to get the limit of, as x approaches infinity, of the natural log of 1 plus 2 over x divided by 1 over x. That's what we've been doing in all the previous questions. So if we put in x right now, we're going to get the natural log of 1 divided by 0, because 1 over infinity is just 0. So we're going to have to differentiate the top and the bottom, right? Use L'Hopital's rule. And when we're differentiating the natural log of 1 plus 2 over x, it's going to be, so that's going to be the limit as x approaches infinity. That's going to be, well, remember the natural log of x is 1 over x. So the natural log of, or the derivative of the natural log of 1 plus 2 over x, that's going to be 1 over 1 plus 2 over x. But remember, we have to multiply by the derivative of the inside, right? That's that chain rule. So we have to multiply it by the derivative of 1 plus 2 over x. So the derivative of 1 is just 0, and the derivative of 2 over x, just for time's sakes, it's going to be negative 2 over x squared. Okay, and we're going to be dividing all of that by the derivative of 1 over x, which is just negative 1 over x squared, if we use our power rule. Okay, so now what we're going to do is we're going to make this a bit simpler. So the limit x approaches infinity, it's going to be, we can bring this out and multiply it. So notice how these negatives cancel. And it's going to be, so it's going to be 2 over 1 plus 2 over x, I believe. Yeah, 2 over 1 plus 2 over x. Okay, now what we're doing is we're taking the limit as x approaches infinity of this. So if we plug in infinity for x, this is just going to give us, so the natural log of y is going to be 2 over 1 plus 2 over infinity. And 2 over infinity, anything over infinity, if it's a constant, is just 0. So it's going to be 2 over 1. And 2 over 1 is just 2. So we know that the natural log of y is 2. And we know that the natural log just means the log in base e of y, which is equal to 2. So now we can get this into exponential form. So e raised to the power of 2 is y. So that just means y equals e squared. And remember, we started with y on the left side, and we just took the natural log of it. So e squared is going to be our limit. So yeah, these can for sure get a bit crazy. We have to do some algebraic or differential manipulation, but in the end, we are able to solve them using L'Hopital's rule, just getting them into quotients. So it's a similar concept, just a bit more manipulation and kind of tricks we got to use, maybe make it an equation, that type of thing. So I hope this was helpful, and I'll see you in my next video.